Namaste, Shubhodaya, and a warm welcome to the viewers for the CSIR sponsored, CSIR-4PI organized Vismaya Vigyana lecture series season 2. Today is the day 2 lecture of the Big Data Seismology. Thank you for all the support shown by the student community for the day 1. The link shall be posted in the description box in case you want to visit it once again. Let's have a small recap of the previous session. In the last session, we introduced the term seismology, which literally means the study of the various strata of the Earth's crust, as well as the dynamics of the earthquake slip processes. It accomplishes this by employing Earth-passing ground vibrations. The previous session covered the historical development of seismology as a science and how it has transitioned into big data era. Additionally, the definition of big data seismology was explained to the students. So without any delay, let's welcome back Dr. Anil Earnest to the webinar. Hello, Doctor.
Thank you.
How are you, sir?
Thank you. Fine. I will directly go to the talk.
Yes, sir. Yes, sir. You may.
Yeah, yeah. Thank you.
Thank you, sir.
So, welcome back to the second day of Big Data Seismology talk, which is part of a series. Before going into any of the details, I will just again brush up our objectives on conducting this series. The objective of this series is to provide an overview on the emerging field of big data seismology and its importance in geophysics. This is a three-part series which aims to introduce the concept of big data seismology and its relevance in the field of seismology, discuss about the volume, velocity, and variety of seismological data and the challenges involved in managing and processing this data, explain the role of big data technologies in seismology, including cloud-based storage, distributed computing, and high-performance computing, highlight the applications of big data seismology, including earthquake detection, seismic imaging, seismic hazard analysis, and early warning systems, provide case studies of real-world applications of big data seismology and the techniques used to analyze and process seismic data, and outline the future directions and opportunities for research and development in the field of big data seismology. Last week we discussed on the introduction on the concept of seismology, and then we looked at the history of seismology and its evolution as a big data science, and briefly on the definition of big data seismology. Today, we will be looking at how seismological data acquisition is done and traditional methods of data processing in seismology, and then on what is the difference between passive and exploration seismology, and how have advances in seismological methods improved subsurface imaging, and what is the big data and how is it being used in seismology, and what are the main drivers of big data seismology. First, we will look at seismological data acquisition. It involves the collection and recording of seismic signals generated by earthquakes, explosions, and other sources. The following are some of the methods used for seismic data acquisition, like instruments like seismometers. Then there are networks called seismic networks, and there are arrays called seismic arrays. There are instruments called borehole seismometers, ocean bottom seismometers, infrasound sensors, etc. And data acquisition normally requires careful planning and execution to ensure that the data is accurate and reliable. And it's important also to consider factors like instrument calibration, sensor placement where it is placed, and data quality control to ensure that all the data is suitable for analysis and geophysical interpretation. Actually, it's very hard to measure the ground motion using an instrument, as the instrument which does that must also move along with the ground. So to resolve this, seismometers contain a mass on a spring that remains stationary and helps measuring motion of the instrument relative to that mass. Early seismometers were entirely mechanical. Advancements in electronics helped us to keep the mass fixed and therefore record a much wider range of frequencies. An ideal seismometer nowadays can record accurately over a broad range of frequencies and a wide range of ground motion amplitudes without going out of the scale. Seismic networks encompasses the use of advanced computing and data analysis methods to process vast amount of seismic data generated by seismometers in real time around the world, with the aim of improving our understanding of earthquake processes, predicting seismic hazards, and developing early warning systems. Figure shows the distribution of global seismographic network manned by different agencies and actually compiled as a unitary facility. Seismic arrays are actually system of equipments, seismographs, which are placed spatially and temporally distributed over a space region, and this actually helps in improving the resolution, spatial resolution and temporal resolution of data acquisition. Left hand side shows the US Earthscope network, which do have a fairly good spatial resolution covering the entire continental United States. Right-hand side shows the network distribution of Indian Seismological Network manned by National Center for Seismology at New Delhi. It do have a well spread coverage all over India, starting from south to north and from Lakshadweep Islands to Andaman Nicobar Islands from west to east. Interestingly, India is also coming up with a very high dense, continuously operating reference network by Survey of India. The map shows its spatial distribution, and it's still in its installation, testing, and operational phases. So once it is fully operational, India will be having a very high dense network of looking at the seismic activity happening within our premises. Borehole seismometers are equipments which are seismographs which kept at within inside boreholes up to depths of few meters to few hundreds of meters. This actually helps in reducing the other cultural noise in the surroundings and other ambient or anthropogenic noise sources in the vicinity. Ocean bottom seismometers, as very clearly seen in the figure, right hand side bottom below, is actually sensors which placed on ocean basins, which are actually connected to a surface buoy so that the data can be transferred to a satellite network, to a land station server, or to nearby vessels so that data can be fetched later at time to the land station servers. Something similar, infrasound sensors are also there that which actually sense the infrasound um, um, perturbations generated out of earthquakes. Now going to check about the traditional methods of data processing in seismology. First is signal pre-processing. This step involves filtering the raw seismic data to remove noise and unwanted signals. Common filtering techniques include bandpass filtering, which passes only a selected frequency range, and high-pass filtering, which removes low-frequency noise. Second is event detection, which involves identifying seismic events such as earthquakes, explosions, or other sources in the data. This is typically done using automated algorithms that identify significant changes in signal amplitude and frequency. Next is event location. Once events are detected, their location must be determined using seismic data from multiple stations. This is typically done using triangulation, where the arrival time of the seismic waves at each station is used to calculate the location of the event. Next is characterization of the event itself, which involves analyzing the seismic waves to determine their magnitude, duration, and other characteristics. This is typically done using a combination of manual and automated analysis techniques. Looking at this process, then further steps are archiving of the data, which is typically archived in a central database for future analysis and research. Traditional methods of data processing in seismology can be time consuming and require significant manual input. However, they are still widely used to do their accuracy and reliability. In recent years, there has been a shift towards the use of big data techniques such as machine learning to automate some of these tasks and improve the efficiency of seismic data processing. The pre-processing step, this slide particularly shows the pre-processing step, how bandpass filters or filters are passed over the raw data so that we can actually get a clearer picture of the earthquake event itself. Event detection actually helps us to find out when exactly the nucleation of the earthquake or a explosive source happened. The left-hand side shows a typical earthquake seismogram, whereas the right-hand side shows how an artificial explosion may look like. where the magnitude of the body waves will be larger than that of the surface waves. As I earlier talked about, triangulation techniques are used for finding out the exact location of the source location of the earthquake. Here in the figure, it shows that those triangles are some seismographs which detected some earthquake from central part of the location. And using triangulation technique, we came out with where the intersection of the all the ranges of the respective seismographs, which actually represents the source location, or otherwise called as the epicentral location of the earthquake. Now, we will look at what is the difference between passive and exploration seismology. Passive seismology is basically about recording the seismic waves generated by natural sources or existing sources like earthquakes, which are basically due to fault motion. Exploration seismologists, basically what they do is that they generate their own seismic waves using artificial sources like explosion, because they can control the timing and location of the source of the seismic waves. They can work with large number of instruments at a time, and that can be deployed for a short period of time. But earthquake seismology, passive seismology is mostly used for R&D purpose, like earthquake seismology studies to understanding the earthquake physics and all. But exploration seismology is mostly widely used in oil industry to understand about the subsurface structures, especially oil-bearing bodies. So how have advances in seismological methods improved subsurface imaging? I will just go to one single example called full waveform inversion. Full waveform inversion uses the full seismogram for imaging, trying to match the data and model rather than only using simplified measures like travel times, and thus provides better image resolution. Right hand side bottom below, we can see the full waveform inversion solution of a stack of seismographs, which actually shows clearer picture of the subsurface than any other better known techniques available earlier. So what is big data and how it is being used in seismology? Big data is a related term that defines data containing greater variety with larger volumes or coming at in a faster rate, which requires different data analysis strategies and technologies than using the earlier days techniques. In seismology, the volumes of data being acquired from individual experiments are now reaching hundreds of terabytes in passive seismology and petabytes in the case of exploration seismology. The velocity of data is the rate at which it is acquired or analyzed. In seismology, a new measurement technique called distributed acoustic sensing can fill a 1 terabyte hard drive in approximately 14 hours. The variety of data being used for seismic investigations is also increasing, with complementary data types like usage of GNSS, barometric pressure, and infrasound becoming more commonly combined with seismic data. As already said in the last talk, big data seismology is a subfield of geophysics that involves the application of big data techniques and technologies to manage, process, and analyze large volumes of seismic data. So now we will look at the main drivers of big data seismology. There are theoretically three main drivers. First, innovations in the sensing systems are allowing seismologists to conduct big data experiments. Two, new data-hungry algorithms such as machine learning and deep neural networks are enabling seismologists to scale up their data analysis and extract more meaningful massive seismic data from massive seismic data sets. Third, advances in computing are allowing seismologists to apply these data-hungry algorithms to big data experiments. In addition to this, parallel and distributed computing allows scientists to perform many computations simultaneously, with calculations often split across multiple machines, and cloud computing services provide researchers with access to on-demand computing power. So now we will look at what exactly this big data seismology involves. The left-hand side image shows that it's basically an intersection of all these large data sets, then high-performance computing and new age algorithms. The field involves the integration of traditional seismological methods with modern big data technologies such as machine learning, distributed computing, and cloud-based storage to enable rapid and accurate analysis of seismological data. So this new age technique actually gives newer insights on other processes like earthquake process itself, or in the field of exploration seismology or tomographic imaging or non-earthquake sources and monitoring hazards. Now we will look at the importance of big data seismology in geophysics. It's becoming increasingly important in geophysics for several reasons, as the volume of data it generates and the volume is rapidly increasing due to the deployment of dense seismic networks and development of newer technologies. Big data techniques are necessary to manage and process this large volume of data. Next is complexity of the data. Seismic data is, as it is, very complex and heterogeneous, consisting of various types of signals with different characteristics. Big data techniques such as machine learning can be used to extract valuable information from this data that may not be immediately apparent to or easy for human analysis. Next is speed of analysis. Traditional seismological analysis methods can be time consuming and require a lot of manual input. Big data techniques can automate some of these tasks, hence allowing for faster and more efficient analysis of seismic data. Big data seismology is again becoming increasingly important in geophysics because of many multitude of reasons, like early warning systems. Big data seismology can be used to develop early warning systems for earthquakes, providing critical information to emergency responders and to the public in event of an earthquake. Seismic hazard assessment. Big data seismology can be used to assess seismic hazards in different regions and to develop earthquake-resistant designs for infrastructure and buildings. Overall, it has the potential to transform the field of geophysics by allowing more for accurate and efficient analysis of seismic data, leading to improved earthquake prediction and seismic hazard assessment. Now we will look at the volume, velocity, and variety in the case of big data seismological data sets. The volume, velocity, and variety of the seismic data are significant challenges facing the field of seismology. These three factors are often referred to as three V's of big data and can make it difficult to process and analyze seismic data using traditional methods. 1. Volume. Seismic data is generated continuously and in large quantities, particularly in regions with high seismic activity. This data can quickly accumulate, making it challenging to store and process using traditional data analysis or processing methods. Velocity. Seismic data is generated in real time and requires rapid processing to provide timely information to decision makers. Delays in processing can impact the accuracy and usefulness of the data as well as to the life and infrastructure in our vicinity. Variety. Seismic data is generated from variety of sources, including earthquakes, explosions, and other sources. The data can vary in frequency, amplitude, and other characteristics, making it challenging to process and analyzing using traditional methods. To address these challenges, seismologists have begun to adopt big data techniques such as machine learning, AI techniques, and cloud computing. Now,
Sir,
challenges in managing.
Anil sir, just
Yeah,
increase the volume of your system to max.
yeah, that's that's maximum only.
Okay, sir.
Yeah. Challenges in managing and processing seismic data. There are several challenges in managing and processing seismic data, including data volume. Seismic data is generated continuously and in large quantities, resulting high volume of data that needs to be stored and
Speaker's
processed.
experience with the
Data
song
velocity.
because in that system
Seismic
who is
data
this
needs to be
content
processed and
automatically applies. Yes,
analyzed in
just one
real
minute.
time,
That's
making
all.
it challenging to manage and process. Data variety. Seismic data is generated in from various sources and in different formats, making it difficult to integrate and analyze. Data quality. Seismic data can be noisy and contaminated, leading to issues in event detection, location, and characterization. Something similarly, computational requirements are also there called that seismic data processing requires significant computational resources, making it difficult to process and analyze using traditional methods.
Expert is also needed in processing. Specialized expertise is needed and knowledge of seismology, making it challenging to find qualified personnel to manage and process the data. Now we will look at the role of big data technologies in seismology. Big data technologies such as machine learning, artificial intelligence, and cloud computing play a crucial role in seismology by providing new tools and methods for managing and processing seismic data. The following are some of the ways in which big data technologies are being used in seismology. 1. Data processing and analysis. Machine learning algorithms can be used to analyze large volumes of seismic data and identify patterns and anomalies. These algorithms can improve the accuracy of earthquake detection, location, and seismic event characterization. Early warning systems. Big data technologies can be used to develop real-time earthquake early warning systems. These systems use data from seismic networks to detect and locate earthquakes and issue alerts to people in the affected areas. Next is cloud computing. Cloud computing platforms provide scalable and flexible computing resources that can handle the high volumes of seismic data generated by seismological networks. Cloud computing also enables data sharing and collaboration among geophysicists around the world simultaneously. Data integration. Big data technologies can integrate seismic data from multiple sources, including satellite imagery, ground-based sensors, social media, and to provide comprehensive picture of seismic events. Disaster response. Big data technologies can be used to predict the impact of earthquakes and other natural disasters and plan for response and other recovery efforts. Overall, the use of big data technologies in seismology can lead to an improved understanding of seismic events and better preparedness for earthquakes and other natural disasters. Here we comes to an end of today's talk, and next week we will be discussing about case studies of the real-world applications of big data seismology and future directions and opportunities for research and development in the field of big data seismology. Thank you.
Thank you, Anil sir. It was a very like, how do I say it, a small and yet very powerful talk. Thank you. So we will wait for about 30 seconds again to see.
Yeah, okay.
So actually majority of people have joined now. So I think we might get the questions later. So
Yeah,
once I get the in the email box, then I will forward it to them. That would be the better. Okay, so as of now, there's no questions. Thank you, Anil sir. Thank you once again. So in next week, you've already said what you're going to discuss. So can't wait for the next week. So see you next Thursday at same time. In the meantime, please do like, share, and subscribe our channel. Thank you. Have a good day.